Hello everyone. In this video, which is my first video of GD&T series, we are going to talk about this very important topic in the industry, GD&T, which stands for Geometric Dimensioning and Tolerancing. So when you design a part or several parts and you want them manufactured, and then again, if it's an assembly, put together and then inspected before put together to make sure everything is functional, you want to transfer or convey the design intent to the manufacturer and to the inspectors in a very clean and yet effective way, so that they can perform their job with minimal need to repeat the production, to repeat the inspection, and to basically avoid higher costs of manufacturing and inspection that are not necessary. And that's where you use GD&T and GD&T symbols, okay? So it is basically a part of overall drafting and technical drawing language. And the main goal of it is really functionality, okay? The main goal of it is to make the job of a designer, manufacturer, and inspector easier and avoid unnecessary cost and unnecessary reproduction and reinspection of the parts. So let me give you an example here. Let's say here you have, let's say this mirror or whiteboard or any object, and it is going to be assembled inside the wall like this. So there is an area of the wall, there is this pocket, and you're going to put this mirror into that pocket and assemble it. Now, the size of this area in the wall is fixed, okay? It is about 1500 mil by 900 mil. And the depth of this pocket here that exists is about 5 millimeters, okay? So the depth of the pocket is 5 mil. Now, this is fixed, this is given to you. What you need to make is this mirror. So what would you say? What you can do is, when you provide the views for this mirror to the manufacturer, you say, hey, the length of this mirror ought to be very close to 1500 mils. If it's a little bit more than this or a little bit less than this, then I have to do some extra things for the assembly, right? For example, if it's much bigger than 1500, and by much bigger, I'm not talking about several hundred mils, maybe even 10 mils. If it's like 1510, then the size of this pocket is definitely not 1510, it's less than 1510. So I have to either cut the wall or break the mirror. Both of them are not easy operations, especially the mirror. Or I have to manufacture the mirror again because it's not going to fit. The same thing with the height. It is 900. Do not make it much longer than 900. On the other hand, do not make any of those dimensions much shorter, because I really do not want big gaps to exist between the mirror and the pocket on the wall. So you provide these dimensions 1500 and 900 with the maximum amount of deviation you can have from these, what we call nominal dimensions, these 1500 and 900, we call them nominal dimensions. You say as long as the actual or true dimension is plus or minus 2 mil away, deviated from the nominal dimension, I'm okay. I can put it together, okay? If it's out of that range, forget it. I cannot do that, right? So you provide this dimension and the tolerances on the dimensions, the linear tolerances, to tell the user, the manufacturer, what is it that they need to do. So again, let me put some terminologies for you here. This 1500 and this 900 are what we call the nominal some people might call them the true dimensions. This is what you ideally want to get. Now, in the world of manufacturing, nothing is perfect, nothing is ideal. You always get a little bit of deviation because of the machine errors, because of the operator errors, and so on. So, as I said, maybe at the end of the day, the mirror that they give you is like 1501 mil, and this guy is like 899 mils, correct? So if it turns out to be those dimensions, can you use it? You come and compare those dimensions against the allowed tolerance, and you say, yes, this here means it is between 1502 and 1498, and since this dimension belongs to that range, this is good. The same thing for this one, 900 plus and minus 2, so that dimension is between 898 and 902. Again, it belongs to that range, so this dimension is good. And when that's the case, we say the part is in spec. Or specs. The part is okay. So this is if you only cared about what? The height and the width. Now what about the thickness? Well, here, as I said, the depth of this pocket that I have on the wall is 5 mils. So even if this thickness of this mirror is up to 5 mils, I should be still able to put the mirror in that pocket and have the mirror be flush or below the surface of the pocket and have no problem. Right? But here, since I really want the mirror to be below the surface of the pocket, I say, well, the thickness that I want is 2 mils plus and minus 0.1. Okay, so I want some gap to exist between the edge of the mirror and the edge of the outer edge of the pocket. Good, and it works if, let's say, now you get what? You get 2.5 mil thickness out of the factory, right? Then you say, well, look, I wanted it to be between what? Between 2.01 and then what? 1.99. This number is clearly not in that range, so I'm going to reject this part. And I say, well, that's not what I wanted. And why? Because it doesn't fit my thickness tolerance. But does that dimension really matter that much? Remember, you have 5 mil of what? Of room to squeeze this mirror in, and this 2.5 is below that 5 mil. So it is a very good straight mirror. It works just fine. It fits inside the pocket. If they made it a little bit thicker, ideally you should not reject this. This is a functional mirror. Making it again means a lot more cost. So maybe this tolerance that you put in it, 2.01, is a little bit too tight. Maybe I should not go with 2 plus minus 0.1. Maybe I should go with 2 plus and minus 0.5 or something, right? Or I can change this middle number. Instead of 2, say maybe 3 or something, because this guy can go up to 5. Good? So tight tolerances can lead to rejecting some of the parts that could be what? Functional, and the ultimate goal of this GD&T is to make sure the part is working and functional. Now, on the other hand, if they give you a mirror that is not straight, they give you a mirror that is curved like this, it's convex or concave. And you don't want that. You want a straight mirror, right? You don't want the picture of you in the mirror to be what? Look a lot bigger or a lot smaller. You want a straight mirror. if they give you a mirror like this, and the thickness of it is 2.1, which is within the spec, at the boundary of the spec really, but still within the range, and the span of it 901.2, which belongs to this range, then you say, well, this mirror is good. They did some measurements, they found the thickness is good, the width and the height are good, so that's a good mirror. While this guy is not functional because it's curved, and it's not going to show the size of objects the right way. It's going to show them smaller or bigger. So you're rejecting something that should be good because there is room for it, and you are accepting something that is definitely not functional just because it is staying within your tolerance values. So that means this way that you tolerance your thickness is not really a functional and good way to do the tolerancing. So what would you do? Instead of showing the thickness like this, because you do not want a curved mirror, you show it a little bit differently. You say, hey, this is the width and the height, that's good. For my thickness, I allow more deviations from 2. So as long as it's between, let's say, 1.5 and 2.5, I still accept it, right? But since I want to make sure the form, the shape of it is not curved, I add something called basically the flatness here. So I add this geometric tolerance, which is called flatness. And I said this guy ought to be flat with a tolerance zone of 0.02. So this number here is what we call a tolerance zone. And the meaning of this is different than these other numbers like plus minus 2 or 900 or so. So what's the meaning of that? The meaning is this. If I look at the curved profile of this mirror, and if I draw two flat planes, two straight lines, such that any point of this curved profile falls within those two planes, so they completely contain your the gap, the zone between the area between these two planes, completely contain your profile. The gap between these two should not be more than 0.2, okay? And of course, the smaller you make that gap, it means the closer they are together, so it means your profile should be closer to a perfectly straight shape. Now, in these videos, we are going to follow the rules in ASME Y14.5 standard, American Society of Mechanical Engineering standard, not ISO. And finally, just wanted to show you a brief list of GD&T symbols. We try to explain them one by one through the videos we are going to generate. But in general, you can break them down into 5 or 6 categories: form, position, orientation, runouts, and profile, or you can separate runout and profile. The material modifiers, LMC and MMC, and then some other symbols that you have. And as I said, the goal is to explain them one by one. So this is our first video. Thank you for your attention, and I will see you in my next video. Thank you.